everyone. This is Jyoti Sharma once again presenting you the presentations on electrical machines, which is unit 4 of the subject Basic Electrical Engineering, having the subject code of KEE 101 or 201 according to AKTU. Okay, so in the previous lectures, in the lecture 3rd regarding the DC machines, we have seen the various kinds of DC motors, their constructions, their working principles, their characteristics, torque versus speed characteristics, torque versus armature current, right? Based upon that, we have seen that the DC shunt motor, DC series motor and the compound motor, let it be differential or the compound, cumulative, in that we have seen that the maximum starting torque, or I must say the maximum amount of the starting torque is produced by the DC series motor, right, where the torque is directly proportional to the armature current square, right. So it will be holding good in the applications where where you require the starting torque to be high. Likewise, the pulling or the lifting jobs, likewise elevators, lifts, hoists, cranes, right. So these kinds of applications are found for DC series. Likewise, in DC shunt motor, we have seen it is characterized by a fairly constant speed, right. There used to be a very minimum amount of decrease in the speed with the load, right. Otherwise, it is fairly constant. That too, it is a constant flux motor as well, right. So it will be finding its applications where the speed required is almost constantly, fairly constant, right? It can be fans, blowers, drilling, milling, right? All these motors, pumps. So there we can have the applications. Once again, coming to the compound, cumulative and differential. Once again, cumulative, it is having the advantage of both, right? It is having the advantage of series, where it can be started at no load condition, right? And also it gives us a very moderate starting torque, right? A good starting torque, right? So it will be having the applications compound which is comprising of both. Likewise, elevators, lifts, always, and it can also be including the rolling, milling and the pumping actions, right? But the differential compound motor, right? In this case, it gives us the reverse characteristics. What we have seen with the increase in the load, the speed also increases, right? Which is undesirable, because there is always a constant decrease in the flux, right? That's why this kind of motor is not practically being used, differential compound motors. Now coming to the AC motors, broadly classify, if at all I broadly classify all the kinds of electrical machines, it can be either AC, DC. DC we have seen in the previous 3 lectures, right? Now coming to AC, once again, the AC motors can be either 3-phase or it can be single-phase. Coming to the very first motor, that is the 3-phase induction motor. So what we are going to see in our lecture 4, that will be the principle of working of 3-phase induction motor, right? Then its principle involves the production of rotating magnetic field. So what is this basically rotating magnetic field is and how it is being produced, right? So that's production of rotating magnetic field. Then the construction, how the construction of 3-phase induction motor goes through, what is the stator part, what is the rotor part, we'll be seeing that. Then the slip and its effect, the torque equation for a 3-phase induction motor, it is an induction motor, so obviously the torque equation is very important. And how does this torque varies with the slip, right, or the speed in turns. So we'll be seeing that. So coming to the very first topic, that is the working of 3-phase induction motor. Now, as we know, any rotating machine, right, that consists of 2 parts. One is the stationary part, which is being called as stator, and the rotating part, which is being called as rotor, right. Same way, in case of 3-phase induction motor, we used to have stator, rotor. The stator of the motor, that consists of the overlapping windings offset by an electrical angle of 120 degrees. When we connect the primary winding or the stator, right, to the 3-phase AC source, it establishes a rotating magnetic field which rotates at synchronous speed. What is the synchronous speed? We'll be once again discussing that. The synchronous speed, it is being given as 120 F by P. 120 F, it is just proportional to the supply frequency and inversely proportional to the number of poles of that particular motor, right? So this is synchronous speed. So the rotating magnetic field has been established. Now, according to the Faraday's law, an EMF induced in any circuit is due to the rate of change of magnetic flux linkages. As the rotor winding in an induction motor are either closed through an external resistance, in case of, we'll be seeing in case of say slip ring induction motor, or directly short circuited by the help of end rings, right, and cut the stator because of the shorted end rings, it cut the stator rotating magnetic field. So an EMF is induced in the rotor copper bars, and due to this, this EMF, a current flows through the rotor conductors, right? So here, the relative speed between the rotating magnetic field or the rotating flux and the static rotor conductors is the cause of the current generation, right? Hence, as per the Lenz's law, we know that the rotor will rotate in the same direction so as to reduce the cause. And what is the very cause of producing this rotation? That is the relative velocity between the rotating magnetic field and the static rotor conductors, right? So because of that, the rotor will rotate in the same direction as that of the rotating magnetic field so that the relative motion between the two can be resolved. Thus, from the working principle of three-phase induction motor, it can be observed that the rotor speed should never be reaching the synchronous speed produced by the stator. Although it will be rotating in such a fashion to reduce that relative motion and try to attain that speed, but that is not possible. If that speed is being achieved, or if the speeds become equal, there would not be any relative speed between the two. If there is no relative speed, there will not be any induced EMF in the rotor, the current will not be flowing, so therefore there will not be any torque. So consequently, the motor cannot reach the synchronous speed. So the difference between this stator speed, although the stator is not rotating, it is stationary. So the field which is present over there, what do you call it as? The rotating magnetic field, right, which is rotating at a speed of synchronous speed, and this rotor speed, that is being called as slip. The difference between the two. The rotation of the magnetic field in an induction motor has the advantage that no electrical connection needs to be made to the rotor. Okay. Now, what is this rotating magnetic field is all about, right? We are discussing that when you give a three-phase AC supply to the stator, there would be a production of rotating magnetic field. How this is being produced? And why it is so that it is being produced by only three-phase supply? Can't it be produced by single phase, right? We'll be seeing that. Okay. Now, when a three-phase winding is energized from a three-phase AC supply, then a rotating magnetic field is produced. This field is such that its poles do not remain in the fixed position on the stator, but go on shifting their positions around the stator. That is the reason we used to call it as rotating field. This is very much synchronism, very much, I must be saying, synonymous to having your poles being rotated with a certain speed, right? Physical rotation. A three-phase induction motor that consists of three-phase winding as its stationary part being called as stator. The three-phase rotor stator winding is connected either in star or in delta. The three-phase windings are displaced from each other by 120 degrees, right? So when it is being supplied from a balanced three-phase AC supply, then the three-phase currents flow simultaneously through the windings and are displaced once again by 120 degrees, right? Each alternating phase current produces its own flux, which is also sinusoidal. So all the three fluxes are sinusoidal and are separated once again by 120 degrees, right? So we know that if the phase sequence of the winding is being given by RYB, we do know what is the significance of phase sequence and what is this phase sequences. It is the sequence in which the individual phases of a three-phase supply system attains their maximum, positive maximum or zeros, right? So if the phase sequence is RYB, then the mathematical equations for the instantaneous values of the three fluxes, what will be the three fluxes? Phi R, phi Y, phi B. So phi R, because this comes at the first for the phase sequence, so it can be given as phi m sin omega t. right? Phi y displaced by 120 degrees. So, phi m sin omega t minus 120. Phi b displaced by another 120 degree, that means minus 240, right? Obviously, we can represent that in the phasor, in the waveform, right? Phi r is the most leading one, then phi y, then phi b, right? Now, if at all, I can even represent these in phasors, right? If at all, I need to represent this in phasor. So, this is my reference phasor, phi r, right? After that, 120 degree, I'll be having my another phasor, that is phi y, lagging the first one by 120 degree or displaced by 120 degree. RYB, the third one, once again phi b, it will once again be displaced by 120 degree, here, right? Considering these to be the positive values or the positive directions of the three phasors. So, I can even represent that in phasor form, right? Now, what we are saying is, if we give this three-phase AC supply to the stator, right, there will be a production of rotating magnetic field. That means at every instant, at every omega t, at every instant of this theta or of omega t, I'll be having a resultant flux, right? That resultant flux is the phasor addition of phi r, phi y and phi b, right? So, we'll be finding it out at various thetas or at various instants, what will be the value of this resultant field, right? So, coming with the very first case, if the case 1 is when omega t is equals to 0. So, what we need to do? Just substitute your omega t as 0, right? So, phi r, that is going to be phi m sin 0. So, 0. Phi y, phi m sin omega t minus 240, omega t, 120. Omega t is 0. So, that is minus 120. Its value will be minus 0.866 phi m, right? Similarly, phi b, that is going to be positive 0.866 phi m. So, let us see it in phasor. Where would be the three corresponding phasors and where would be the resultant? Okay, phi r is 0. This used to be our reference, this used to be our phi r, but that is 0. So, we will not be showing that. Phi y, that is negative, but the positive what we have shown was over here, right? So, the negative of this phasor would be shown just opposite to it, right? Here. This is phi y, which is representing negative of 0.866 of the maximum value of the flux. Phi b, that is positive of 0.866 phi m. We have taken it over here. So, that is going to remain same. So, where would be the resultant? The resultant of this phi r is 0. This is not with us. So, the resultant of the two is the phasors addition of phi y negative and phi b, right? So, obviously, the resultant will lie over here. So, this is the resultant. This is the resultant which I have shown with the green, right? What will be the magnitude of it, right? The magnitude that can be very easily known. You know that this is a balanced supply system, so all of the four are going to be same. So, if at all, I'm going to drop a perpendicular from here to this resultant, it is going to lie exactly at the center, right? Say this is O, A, B and C, right? So, obviously, what will be this angle? AOB, this is going to be 30, right? How can I give cos 30? Root 3 by 2 obviously, but that can be given by from the triangle OAB, that is OA upon OB. Once again, what is OA? OA is half of OC, right? What is OC? OC is my resultant phasor, right? Okay. And OB, that is if you just see, that is minus of 0.866 phi m, right? And what is cos 30? Root 3 by 2. From here, if you just find out how much is OC, that is the resultant what I want. So, you will be getting the value as 1.499 phi m, or which I equated as 1.5 phi m. So, the resultant flux, this is phi r, I am writing it as resultant. So, the resultant flux what I will be getting, or the resultant feed I will be getting, that will be 1.5 times the maximum flux what was there in the alternating or the sinusoidal wave, right, of the input wave. Similarly, this is, and where is the direction? Direction is just upward. Going for the another instant, say at instant omega t is equals to 60, the same process. There Phi r would be phi m sin 60, so that is 0.866 phi m. Phi y minus 0.866 phi m, and phi b, obviously it is going to be minus 180, so 0, right? Now for this, if you just see here, now phi r, that is positive, so we have gone for this. Phi y is once again negative, right? This was the positive, so phi y negative is once again upward. Phi b, that is 0, so we need not to represent that, right? Once again, the resultant would be of these two, so the resultant will lie over here. You can see that once again, you know, it's a symmetrical system, so once again all the four are equal. If at all I want to have the magnitude of this resultant flux, once again I'll have a perpendicular being dropped over here. Same calculations, the angle is 30. Once again I'll be having the resultant flux being produced as 1.5 times the maximum flux. But it can be seen, right, that the magnitude is remaining same. Here also I was having 1.5, here also I'm having 1.5 of maximum, but the direction of the resultant field has shifted. Earlier it was just perpendicular, I must say just upward. This time it has been shifted by 60 degree. Another case 120. Same way, if at all I see with 120, the magnitude is once again 1.5, but it will be shifted down over here, right? At 180, the resultant is once again 1.5 times, but the shifting has been taken place. Similarly, if at all I go on with 270, 360, like that, right? So I'll be seeing that the resultant magnetic field is once again shifting its positions and giving you an interpretation of rotating magnetic field, but it is rotating with a constant magnitude. What is that constant magnitude? 1.5 times of the maximum flux of the input supply, right? But it is rotating, and rotating with the speed of, ns, right? That is how the production of rotating magnetic field is being done. You can see over here is that for the production of rotating magnetic field, every time I require at least two-phase supply, right? Even if one is 0, I require at least two phases displaced by some angle. Then only I can be having a resultant field, right? Which is not present in single phase. We'll be discussing that in single phase although. Now, the speed of the rotating magnetic field, as we were discussing, this is the rotating magnetic field will be rotating at a constant speed being called as synchronous speed. Synchronous to what? Synchronous to the frequency of the supply being given, right, to the stator. So, ns is the synchronous speed given by 120 f by p. F is the frequency of the stator supply and p is the number of poles of the motor. And what will be the direction of this rotating magnetic field? Whether it will be clockwise, anti-clockwise, who is going to decide that? Yeah, the phase sequence, the direction of this rotating magnetic field, that depends upon the phase sequence of the AC supply connected to the stator winding. If we interchange any two phases of the AC supply, or if we interchange the phase sequence of the AC supply, it will be now a new phase sequence, so that the direction of the rotating magnetic field in the three-phase induction motor will reverse. Consequently, the direction of the rotating magnetic field will reverse, as well as the direction of the motor will also get reversed. What is the connection between the two? That can be very easily understood by we know that whatever is the direction of the rotating magnetic field, that is going to be the direction of the rotor, right? The rotor tries to attain the same speed because of the Lenz's law to reduce the relative motion. So, it rotates in the same direction as that of rotating magnetic field, right? Okay, coming to the construction of three-phase induction motor. Now, the three-phase induction motor is a preferable kind of motor. So, it is mostly used in most of the industrial drives because it is very reasonable, vigorous, economical, reliable, right? It is also being called as asynchronous motor because it does not runs at a speed of synchronous speed. You know, we are having another AC motor which is being called as synchronous motor because it used to run always at a speed of synchronous, right? The induction motor that requires a very little maintenance, and also it has a high overloading capacity. Right. Now, constructionally, if at all I see this induction motor that can consist of two parts, stator, rotor. The stator is the stationary part of the induction motor and rotor is the rotating part, right. So, the stator, if at all I come, so it is built up of high grade alloy steel laminations to reduce the eddy current losses, right. It has three main parts, the outer frame, right, the stator core and the stator windings. Outer frame, if at all I say, it's outer body of the motor. So, its main function is to basically support the stator core and protect the inner parts of the machine. For small machines, the outer frame is casted, but for the large machine, it is fabricated, right. Now, stator core, it is built of high grade silicon steel stampings. We can see the stampings over here, stator stampings. Its main function is to carry the alternating magnetic field, which produces the hysteresis and the eddy current losses. These stampings are fixed to the stator frame, right. Each stamping is insulated from the other with a thin varnish layer, right. The thickness of the stamping usually varies from 0.3 to 0.5 millimeter. So, the slots are punched on the inner side of the stampings as shown over here. These are the slots being cutted out. These are the slots, right. Now, the stator windings, the core of the stator that carries a three-phase winding, which is either star connected or delta connected. So, which are usually supplied from a three-phase supply system. The 6 terminals of the windings are connected in the terminal box of the machine. The stator of the motor is wound for a definite number of poles depending upon the speed of the motor. Obviously, if the number of the poles is greater, the speed of the motor would be less, and if the number of poles is less, then the speed would be higher. As the relationship between the speed and the poles of the motor is given by synchronous speed is inversely proportional to the number of poles. So, as the number of poles is increased, the synchronous speed is going to be decreased. So, this is all for today's lecture. The rotor construction, the types of induction motors, their torque equations and working will be studying in next of the lecture. Thank you all.